This will be about unsupervised learning, particularly using autoencoders. I was through the folders that Rebecca shared at File, and I found out that you already had some theoretical background of autoencoders. I think with Rui already provide something to you, which is great. But the first thing that I want to say is that, okay, basically we have two types of learning, supervised learning and unsupervised learning, right? Supervised learning, as the name implies, means that the human, we are responsible for training, for teaching, for telling the algorithm what it is. As it was in the first case, I believe it was what is an hot dog and what it is not an hot dog. And then the algorithm should know this. The problem is that in order for the algorithms to be meaningful, we need to train a lot of data. So we need to have a lot of humans telling the algorithms what is an hot dog and what is not an hot dog, or what is letter A and letter B, or what is a car, what is a person, what is a machine, and so on and so forth. But I believe that this was the first algorithms that was developed. Okay, so we are annotating data. Unsupervised learning, on the other side, is a set of algorithms, of approaches that tries to learn by themselves, right? So they try to understand and try to learn without the human being to tell them what they are learning, let's say. Of course, that this type of unsupervised learning, in my opinion, has some limitations, because it is better for the human to tell the algorithm what it is that we want to detect, let's say. But nevertheless, I also believe that unsupervised learning is one of the ways to go, which is basically we design an algorithm, we design an architecture, we design a model that tries to grasp the learning and try to help us detect things. So what is here in Portuguese is that unsupervised learning is a machine learning technique that uses a set of data sets that are not labeled for training. And being not labeled is important, meaning that the human has not labeled what it is there, right? Some types of unsupervised learning that I also believe that you already discuss on these hands-on tutorials is clustering, right? So clustering techniques tries to clusterize data, tries to divide data, tries to put them, let's say, feature-wise in a groups, okay? This is also important, and it's some sort of unsupervised learning because the algorithm is trying to clusterize based on features. Association rules and dimension reduction. So, but we will focus on autoencoders. And I will pass directly to the architecture, or the high level architecture of an autoencoder. And basically we have three components, three modules that are used to build an autoencoder. And since the autoencoder principle is for a machine learning algorithm or a network or something is trying to learn by itself, basically you can see this as a mirror. Okay, so in the first level, you have the encoder, which tries to codify, to encode the image, the signal, the thing that we are trying to learn by ourselves. Okay, then this goes into what it is named in the literature a latent space representation. Okay, so this is the codification that we are trying to learn. And then we have the decoder. Basically, or many times, the decoder is like a mirror of the encoder. So imagine that we are trying to encode using neural networks. Okay, let's suppose that we have 3 or 4 layers, layer A, B, C, and D for the encoder. The decoder probably will have layer D, C, B, and A. Okay, it will have a mirror layer shape to the output. And we will see a couple of examples that I want you to develop using code, let's say. Okay, so in short, the encoder compresses the entry data, okay, to remove any sort of noise and generates this latent space, okay. The dimensions of the neural network at the output layer are lower or smaller than the number of layers or the number of neurons at the input layer, okay? The decoder uses a representation of the latent space, okay? So also uses this and tries to rebuild with the maximum of fidelity the input layer. So at the end, let's say that this machine learning algorithm will try to match what it produces to the original image and tries to see the error and tries to fine tune the weights of the neural network, right? In order to learn by itself to have the perfect match, okay? Which is the error actually, right? Um, so let's say that a zero error will represent a perfect decoding, right? So if we input the letter A, and we will have a perfect letter A at the output if the error was zero. Of course, that is in 2025 is utopic, right? So it is not yet possible. That's why what we will or what I will try to provide you here in this very short course is an approach. Okay, it's like a first network for each one of the examples. It is not a definitive example. It's not the definitive number of layers, number of weight. You'll need to explore this afterwards. Okay. Okay, so in practical terms, what we need to, or what we want to achieve is something like this, okay? Again, this example here is, if I'm not mistaken, the first or one of the first examples of the autoencoders application, right? Which is, okay, I have an image which is the number 4, X, and I want to, at the output, have some sort of reconstruction of it. So I am learning by myself. That's the number 4. And this is actually one of the examples that we will use because it is one of the available data sets on Keras TensorFlow that we can easily try. Okay. Naturally, that several or after developing or after appearing autoencoders, several types of autoencoders have emerged and been developed, and some variations of it are appearing from time to time. And these are some of the let's say architectures of autoencoders that are present out there. Okay, so the basic one, which is a basic autoencoder architecture that is developed using dense layers. We will use it. Autoencoder under complete, which basically means that the latent dimension or the latent space has a dimension that is lower than the input, okay? overcomplete, which is the opposite, okay, which means that the latent dimension has a number of has a dimension higher than the layer of input. Convolutional autoencoders, like the images and on the convolutional neural networks, and this is actually very good to processing images, right? For instance, for denoising also. Denoising autoencoder. This is very interesting, and we will also try to make one exercise of it. Imagine that you have an old picture, okay? You have an old picture of your grandparents that has a lot of noise. We could use some sort of autoencoder to try to clean the noise, try to sharpen the image. And this could also be used, for instance, to denoise, to clean known images data sets. For instance, imagine that we have a sign, an SCG, we have some signal that we want to denoise. We can also use this. And one architecture of autoencoder that could also be used like this last one, that it is used to generate images. Okay, this is also very useful also for what? For instance, let's assume that we have a small data set of some pieces from industrial production line, and this data set is not enough for us to train and to try to learn something. So we can use generative autoencoders to try to generate more images out of it, and then we can try on a larger data set. Okay, so what type of applications can we use or can we apply autoencoders for? For instance, compacting data. Many times, and the professors of mathematics knows this better than me, we have huge amount of data, huge dimensions. We need to analyze it. We are humans. We cannot. So X, Y, and Z is more than enough. But we have many dimensions, many data, but many times the data has huge of garbage, non-useful data. So we can use autoencoders to try to some way reduce, compact the data without hopefully losing meaningfulness on the data, okay? Without losing knowledge, and putting the data in a shape that we can analyze better, okay? Detections of anomalies. Why do autoencoders are good on this? Because if you remember, autoencoders accept as input good data, so data that we want to train as valid. For instance, number 4. Let's assume that we want to train data with number 4, okay? And we want to detect if a number is not 4, okay? So I can train my autoencoder, let's say, with number 4, okay? And then if I input one number that is not 4, for instance 3, then the error at the output will be very high. Then I know that this is not a 4. Again, I had this on my computer, but then I can provide this information to you if things are not going okay here. And then you can go to Office 44 and knock on my door for the rest of the year until 2026. But basically, this is autoencoders is very good for this, because one of the examples, because I wanted to provide to you non-academic examples. Okay, so I went to the web and I found out more than 5 gigabytes of images of industrial data. And one of the data and one of the examples is you have a bottle production, the ones that like beer or wine, right? So at the end, at the below of the bottle, you have, I don't know how to say the word in English, but o cu da garrafa, né? The butt of the bottle, right? Uh, and that's a blowing process, a blowing industrial process. And sometimes when the compressed air is either too high or either too low, the shape of the bottom of the bottle is not acceptable. So we want to fast process it to see if the shape is okay or not. So we are trying to defect or trying to detect anomalies in an industrial process. Okay. How do autoencoders can help us on this? Very easily, very easily. Uh, we feed the autoencoder with good bottles, a lot of good bottles. Okay, bottles that we, as humans, we know that those bottles are acceptable for production, are acceptable for me to put in some beer or some wine and sell to my clients. Okay, what happens if some bottles have a butt that is not round or has some defects? Again, I will feed this into my autoencoder. The autoencoder will try to reconstruct the original image. Then I will match it with the good one, and I will have a very high value of error. And then I will know that this is not good. I can also use this, for instance, to detect if we are suffering from some heart conditions from the heart, right? So I can make some ECG. I have my pattern. I can feed in a lot of ECG's patterns, good ones, into an autoencoder. I try to learn, or the autoencoder tries to learn. So these are good ones. If not good ones or similar shapes appear, then I can know, or I have more confidence that that might be a not good or non-valid ECG. Okay, so this is also one very good thing that autoencoders applications are good for. Um, why is this also important, and why this type of unsupervised learning is important for this type of data? Because again, for me to use supervised learning, I need to have a good or a lot of data that I need to put humans to put some labels on it, right? So good bottle, bad bottle, okay? But imagine that we are using electrical vibration signals from the vibration of one machine, okay? How often does a mistake or a non-good vibration appears in the data set? Probably could take months, or could take years, or could take weeks. So I need to have a lot of patience in order for me, in the supervised learning, train the data set, try say, so this is an error, this is an error. And this could take too much time and might not be good. But on the other way around, I know what is a good vibration. So, and if it is not a good vibration, might be a problem in the machine. So I can train an autoencoder to check, okay, this is a good vibration. If you find something outside of this, then might be something wrong with the machine. So I'm just giving examples for you to try to understand where autoencoders can be used for. Noise reduction or denoising, right? Again, and one of the examples is like this. So one of the examples is you have some images, good ones, and we will put some noise. So we will ruin the images on purpose. And then we will try to make for the autoencoders to reconstruct originally the image. It's not easy, but it is also possible for us to do this. Data generations. So we can use autoencoders to generate more data based on the data standards, let's say. This is important in my perspective, since with this I can generate more data in order, for example, train another machine learning to do something, okay? And again, as I already spoke at the beginning, I can compress the data space or the data set by trying to extract the main features of the data set and without losing any type of knowledge. Okay, so some of the things that we need to adjust in an autoencoder and we need to do or we need to design or we need to consider in order to design an autoencoder architecture is okay, not exhaustively, but it is, for instance, the number of layers of the neural networks either at the coder and decoder. Okay. I will risk to say this. Lower number of layers, worse results. Higher number of layers, better results, not always. Better results, but longer to train, longer to detect. So what could be the correct number of layers either at the decoder and coder? I would say that it depends greatly on the application. First, it depends on the type of precision, accuracy that you need for your application. Okay. But also, and not less important, how fast you need to detect something. And I will come back again to the bottle production example. I don't know but if you have not seen, you can go to YouTube and you can see some videos of glass bottle production. It is crazy. It is really, 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 really fast. Okay, so the detecting not good bottles very fast, where fast is milliseconds, is important. Okay, so this is a requirement for the number of layers, let's say, that I could put here. Then is the number of nodes on which one of the layers. So it's not only the number of layers, but how many nodes do I have in each one of the layers? Again, in principle, not always. Higher number of nodes, longer it takes, more accuracy, more precision, okay, roughly. And then it is the loss function, okay? So what is the loss function that I will use in order to have, let's say, more accuracy or precision on my autoencoder, and then the space of the latent space. The lower, the greater the compression. Okay, but then I can lose knowledge. I can lose information about my data set. The longer, less the compression, and okay, let's say that I might not take so much potential of the autoencoder. Okay, so then I decided to put here some concepts that you will see in the code, hopefully. That is, okay, we will see something about a function that is activation equals relu. Okay, what does this mean? And what I put here is not by far exhaustive. It is what it is. What are the most used functions? What are the most loss functions? What are the most activation functions? So, but developing activation functions, loss function is also a research topic. Okay, you have I don't know them at all of them. It is impossible. Okay, but you have a lot of them. So that's why that one of the tasks that you could do at the end is try to change and see what happens. Does it take longer to train? Does it behaves better or not? Okay, so you can explore this later on. Okay, and then okay, so you can read this, but again, So this is the standard activation function for the hidden layers of deep neural networks. Then we have another activation layer. So see, you have one and you have another one that is all of these activations try to introduce some randomness into the networks. Randomness, by crazy it might seems, it's good. Not that that's random, of course, but introduction some randomness into the neural networks is actually good. And all of these tries to in some way introduce this. Okay. Then, okay, so these activations are to use, let's say, into the hidden layers, into the hidden layers of the network. You have more. Then another aspect is, okay, we are trying to optimize, we are trying to reduce an error. Okay, so and for that we have different optimizers. Okay, so one of the optimizers that we will use is the Adam optimizer. Okay, it tries to combine good things about different let's say other optimizers. Again, developing an optimizer is also a very good research topic. Okay, so trying to develop an optimizer that allows me to train networks better or faster or whatever. And then as we are training, as we are optimizing, we need to optimize against something, okay, which is the loss function, right? And okay, one of the standard ones is the mean square error, okay, which basically is a function that squares the output versus the input of what I'm putting into the network. Okay, so these are some concepts that I want you to have in mind. But I guess you all already have from the other from the other from the other talks. Okay, so now the idea is to go to some hands-on because all the idea is to go all in hands-on. And for going hands-on, I could have different paths, but I decided to take the hardest one, which is putting things running on your local computer. You don't need to do this. You have different cloud platforms like Google Colab and others that you can put the code there and then you run. Okay. But in that aspect, we are losing feel of how hard it is to deploy an algorithm because things then appear to be like magic, right? So things just run, I press play, and then something happens. And the idea is for you to install things, install packages, have some errors, hopefully not so many. And with that, you also learn. Okay. Okay. So the first thing, and Rebecca already have here, is to install Python and Visual Studio Code. Okay, you can use another programming environment. Visual Studio Code is one very easy. It's free. Everybody's using it. It's becoming powerful. So and for Python, I will ask you because that's why I forgot my computer at home. I was trying to install on a desktop computer and I was installing the latest version, so 3.13, and TensorFlow was not installing. Okay. So I found out that if you install version 3.12, then TensorFlow is installed on Windows. Okay. On Mac, on Linux, I don't know. okay? But for the ones that don't have Python, you just go to the python.org. Okay, so we can create a folder for this class. So I name it autoencoder project, okay? So then I can enter autoencoder project. So it's more or less make dir or create directly. You can name it whatever you want. I name it autoencoder projects, okay? Again, for creating this developing environment, you could use also Miniconda or Anaconda or whatever. Okay. I hope that some of you already know about this. Otherwise, you can go again to the office and then we can speak afterwards. Okay. So the idea is for us to create a folder where our files, where our developing environment will be. Okay. So for you to work on this, on Windows, you can create a folder on File Explorer. On Mac, you can also create a folder, or you can do something like Command Space for the ones from mathematics and so on. You can Command Space, you can hit Terminal, okay? And then you can open a terminal like I have here. Okay, and then you can mkdir and the name of the folder that you want to create. Okay, and then either on Windows or either on Mac, you can do the same thing, which is we need to set up a Python environment. Okay, how can we do this? We can do Python space -m virtual environment, and we will call our environment virtual environment. You can call it whatever you want, but I call it virtual environment. Okay, so moving forward, we need to create these environments again. So in Mac is Python 3. It will set up the environment. After this, you will see a new folder that is named v environment, which is the name of our virtual environment. Okay. And then we can activate it by running this command. And if you notice, then we will have this at the beginning, which tells us that we are working inside our virtual environment, okay? And inside here, we can now use pip to install a set of packages that we will need to make the course, which is pip install, TensorFlow, NumPy, Matplotlib, Pandas, scikit-learn, Jupyter, then probably Rebecca. Can you upload this file to the shared folder for them to have access right now? Okay, then we can install all of these packages. If everything goes well, pip will install all of this, and then we will have our environment ready for working. Then again, in the shared folder, you already have some Python files that we will use to test and run. But how can we do this? So while it installs, we can go to VS Code, okay? And then we can go to File, Open Folder, okay? And then we will open the folder that we have just created. So our autoencoder something, okay? I think I created this in Carbon Matter autoencoder project, okay? Yes, I trust the authors. Okay. And then we can see that we have already our virtual environment there running, or folder, sorry. And okay, everything is installed. I think we have not any error. Everything is installed and okay. Now I will ask again for the help of, oh, I don't need, thank you. Now you can just copy, drag and drop all my Python files to the folder. After you copy all the files, these are the files of the exercises that we are going to develop and try to see bit by bit in a very high level to see. So one of the first files, or the first file that I want you to run just to see if the environment is up and ready to run this, is this file that we call test inicialização or instalação, sorry. Okay, which basically imports TensorFlow, NumPy, Matplot, and Pandas, and we are printing the versions just to see if everything is installed and it is running. Okay, so we are just seeing if everything is okay. In VS Code, if you already have Python, it should be going there and run Python file, okay? When you run Python file, it will open a terminal below where it will use the command Python and will run the file .py, okay? And with this, if everything is running well, it should print here four things, which is the version of TensorFlow, NumPy, Matplotlib, and Pandas. As you can see, Rebecca has already the environment well set up because, okay, TensorFlow is within this version, NumPy also. We have a version, so might not be the last one, should be, but might not be the last one, but at least all the packages are valid to for us to develop. Okay, so now we have the environment set up for running, okay? Which is okay, which is good. Okay, so now let's build. Okay, let's not build because we will take too much time to code unless we used some copilot to generate code, for instance. But let's open the file that it is called basic autoencoder.py. Okay. What we are going to try to see with this. Okay. So the idea is for us to use this data set, the MNIST data set, which is the numbers, the handwriting numbers, the ones, the two, the three, the four, the five, okay, the five and the six, okay? And let's try to build an autoencoder. And the idea is for us at the end, for the autoencoder to reconstruct the numbers, okay? So we will put a 4, you will learn, and then at the end, the decoder will produce a learned 4, a learned 5, a learned 6, okay? And this is what we are trying to do here. For this, and let's go briefly over this, we will use NumPy, Matplotlib, TensorFlow. We will load the data set that is already existing. So it is within a Keras data set. So it is already available online. So when we run this, the algorithm will go and download the data set and will train and load. Okay. One of the things that usually, I would say, almost all of the times or all of the times that we need to do is normalize data. And data normalized usually is something between 0 and 1. Okay? Since we are speaking about image files that for each pixel, let's say, each pixel is represented from a number from 0 to 255, we need to divide by 255, okay? 255.0 because it is a float, only because of that, okay? And after this, we will have in X-train the train data and X-test the data set for testing the autoencoder. Okay? Then I would go to the let's say to the model itself, and what we are going to build is a three-layer encoder. Okay, and if you remember what I spoke about at the beginning, I said that most of the times, not always, but most of the times, the decoder is a mirror of the encoder, right? And you can see these here very basically in this architecture, which is we have a first layer of 128, and if you can see, we will have in the second layer also 128. We have on the middle layer of the encoder 64, and then on the first level we also have 24, okay? This is the encoded layer, and then we will make a mirror, and then the decoded layer will go here. Okay? Then we create an autoencoder that is built on the model of the decoded architecture that we defined. Okay? And then here we pick the autoencoder model and we are compiling. So we are optimizing, and if you remember, we are optimizing using the Adam that I spoke about on the example on the Word file, but we are not using that loss function, we are using another one. But you, for instance, one of the explorations that you can do here is, for instance, changing either the optimizer or the loss function. Okay, then we are trying to fit, and then we will produce some images. Okay, let's put this into run. So running this, sorry. Yeah. So running this, the autoencoder will start to learn. One of the parameters that we put it here is the number of epochs, the number of steps that we will make is 20. Okay. So one of the things that you can change here also is put the number of epochs higher, which will take longer to train, but in principle you will reach better fits, so less error, okay? Or you can put less, and then you are compromising the error level, let's say, at the output. So one of the first figures that comes out is this, which is, in short, how does the loss function evolve over the epochs? Naturally, while we are training and retraining epoch after epoch, means that the loss function, both on the training, on the validation, is going lower, okay? So I close this for moving to the next step. And then, look, What do we achieve? We achieve that, for instance, so we pick here, I think that the code is picking some random input images. So you can see here on top, okay? I believe it's random. I don't remember by head. But then for this image, this is what the autoencoder reproduces at the end. Okay, so you can see that it reproduces a 7. We can see that it is a 7. But I want you to take some attention, for instance, to these 9s. It's not okay. I can see something, and also for this, I don't know if this is a 6 or a 5. Might be a 6 or a 5. I don't know, but it tries to reproduce. Now, on the next example, I think it is using the same data set, but not using this simple architecture, using some convolutional neural networks, which is more complex. It takes more computational power, but since convolutional, so it is matrix multiplication, let's say, okay? In principle, the autoencoder will learn better to output more accurate, more precise data set. So your visual code, so I will close this, sorry. Your visual code will save these images here. So if you open that, you will see the reconstructed PNG file that you can later on check. Okay, so now let's move to another example, which is, okay, the same data set, the same training scheme, the same normalization approach, the same everything, but a different autoencoder architecture, okay? Now we are using convolutional neural networks to produce or to make the layers, okay? Which in principle, since we are using or trying to learn in images, which is the handwriting numbers, in principle should produce better results, but at the cost of a higher computational cost. Okay, so I think it is a convolutional autoencoder. Okay, so basically the same, but we are building the autoencoder in a different way. Okay, so you can see that here we are using convolutional neural networks. And again, if you have time at home, you can try different copy paste more layers, changing the parameters, try to explore. Okay, and many of the times you will produce, garbage at the end, but you can explore. So the same idea, okay, and let's see how this architecture behaves, but using fundamentally convolutional neural networks. Okay, in principle, it will take longer to train, the same 20 epochs, so the same basic fitting or training approach. And this is one of the bad things about running things locally, because we don't have GPU to train, so it will take longer. So you can use one thing to train this faster. One thing is Google Colab, for instance. The other, you can ask Rufino for a machine to train. Okay, so now if you going to see the loss function should be better in this aspect, but I want you to see this, if it opens. Now, let's try to make this smaller. Okay. I don't know if you can see, but on this, the reconstruction is more close to the original than on the previous one. On the previous one is more faded. right? On this one, remember that the objective, the goal is to reconstruct the original, okay? And if you see, so on this 9 is clear, okay? And also on this, okay? I hope that you can identify this, okay? But let's move. If you want, we can move forward. Then you can go to Office 44, and then I can try to explain, and take a coffee, and then I like coffee, and then we can over the coffee work on this. Okay, so since we are moving shorter on time because I forgot my computer, sorry again about that. Probably we can skip one thing and we can go for the denoising one. Okay. But you can try the other one. So denoising, let me go to the denoising one. If you remember, one of the features of one of the applications of autoencoders is try to remove noise from data sets, okay? Try to remove noise from images, try to remove noise from serials. Imagine that you have a sinusoid and you want to remove noise. You can also remove noise using this, okay? So this is what this example will try to do. For that, what we are going to do is, okay, we are going to load again one available data set in Keras, okay, so in TensorFlow. So it is one data set from fashion. It is gray shapes of fashion things, of clothes, of t-shirts, and these type of things. And then we since we are speaking about images, we are building our autoencoder or our denoiser using convolutional neural networks, similarly to the previous example. Why? Because convolutional neural networks, in principle, in theory, are good at processing images, okay? Again, at a higher computational cost. And then we are building similarly as we have done for the other, okay? We are training for 15 epochs, let's say, because if this is okay, but then we are, on purpose, we are adding noise, okay? So we are training the autoencoder with images without noise. So we are training the autoencoder with original images, and then, okay, we are putting some noise on the images, and we are asking the model, look, pick at these noisy images and try to reconstruct the original. Okay, let's see what does it do. And you will see that it will reconstruct, detects more or less the original image. Okay, probably if we explore more the number of layers, the number of nodes, the activation functions, if we change this, the number of epochs that we are using to train, probably we will reach better results, or by sure that we will achieve better results. While this is training, while this is doing things, and because of time, we will not make the last example. What it is the last exercise, and which is actually the best one, which is you go to the last exercise, and all of this code you have on the files, okay? But you go to the last exercise, and I have here a link. Okay. And this is, okay, except only essential. Okay, what it is this? Because what we have here is academic data sets. Okay, is numbers, I'm writing numbers, is fashion clothes, very low graphics, let's say. But I want to have real data sets. And you have images like this, okay? So bottles, pills, nuts, some cutter, okay? And the idea is for us to train an autoencoder to detect anomalies, okay? And the example that you have is for you to detect anomalies in bottles, okay? In these bottles, okay? And it will produce detection. So it will detect a defective bottle. The idea is I use the bottle, so you need to unzip, untar. Training the autoencoder will take much time. Okay, so you need to train at least for, depends of the computer, but 5 to 10 minutes. Minutes, not hours. Come on. Okay, no. But then, okay, after I explain this, you will see my example. So then you copy paste the folder of the files into your folder. I will explain, okay? And then you can try using the bottom. Now, look, what we have here, there is the noisy image. So this is the image that we put the noise. This is the original image. Okay, the second row is the original images, but the autoencoder trained with these images using the training set, right? Then for the testing set, we put some images with noise, and this is the image that we fed into the autoencoder, okay? And this is the reconstructed image. So this is what the image first from this one, okay? So we need to compare. No, sorry. This is the reconstructed. This is the original. Sorry. I swapped. Okay. So this is the reconstructed. This is the original. Okay. We can see pretty much that it identifier, but there are some features that are not here. Okay. And these are one of the things that you can tweak the parameters, right? So, for instance, in the sweatshirt, you don't find link written there. Okay, you are missing details. You are missing details, for instance, in this shirt, because I think you have here open button. Here you don't have. But the beautiful thing is that would you or me know that this is this? I will not. So over a very noisy image, the autoencoder, without me telling it, unsupervised learning, it could reconstruct more or less the original one. So it would be noise. It would remove the noise. Okay? So this is, at least to me, it is a very good. There are some applications very good. This is one of them. Okay? Denoising. Remove the noise from data sets. Being the data set is one. Look, nobody will guess that this is the sheep. Come on. Nobody. Okay? Would guess that this is a sheep. Nobody. Okay? Okay, great. So I have more exercises there that you can explore. Please explore. Please go to my office with a coffee. Okay? Please download the images, and then the ones that you should run is this one, which is the anomaly MVTech. I call this anomaly MVTech. Again, it will read, so it will use OpenCV with some functions to go and read the images to a folder and blah, 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 blah. It will use convolutional neural networks to train and so on and so forth. Important is two things. Okay, many things, many of the parameters that you can explore later on. But one thing is, when you download the file, it is a zip file. It is a tar.gz file, okay? You need to unzip it, okay? To extract it, okay? Then you need to put you could put it on a different folder. But for simplicity of use, just put the folder in the same folder that you created for this course. So inside Autoencoder project, okay? So just put the folder there, okay? And then also important, you name the folder MVTech, okay? Because all of these codes will go and open a folder named MVTech, okay? And we'll get the images from there, okay? Another important thing is this. At some point in time, okay, we are loading a data set, images. As you can see, you have pills, nuts, wood defects, I don't know what it is this, okay? And you need to identify the type of data set you want to try. You have 15 types of data sets. And the idea, for instance, for the bottle is for you to train on the good ones and identify a defective one. Thank you so much.